말로. 그래서 I would say that on the stay option, guessed rely only on the marginal probability. But on the switch option, guest was able to incorporate Monte Hall's decision. 그거야. 그래서 그런 거야. 그러면 처음에 맞은 확률을 3분의 1을 먹은 거고, 두 번째 거는 내 거 처음에 틀렸다. 가정을 했더니 슈어 이벤트가 나오니까 투더드를 먹을 수 있게 된 거지. 처음에 내가 틀렸다는 어썸션을 받아들이니까. 오케이? 이런 문제가 엄청 많아요. 그 커뮤니케이션하고 인포메이션 티어리에는. 예. 예.
I have another opinion. Can I?
Yeah.
So I cannot agree on this solution since there is a reason. So I will give my explanation. I hope it makes sense. So initially I thought this way, like this way, probabilities. But there's a missing variable. There's no consideration of time. This is a process that the guest make. Let's say the situation is given, there's some car behind the door, and given that there's a decision process that the guest make initial decision 1/3 either way, and then secondly that the host opened the door, either way the first decision was car or not, and then thirdly the guest have option to stick the first choice or switch the another, right? So if you want to apply these axioms of probability, you have to show that the probability is time invariant, right? If the probability is changing by time, you can just like multiply and do Bayes rules, just like just following the axiom. You have to prove that the probability and the sample space is time invariant. But I don't think this process is not the case. Let me show you the reasons. So there's like a two side. Like for like guest, initially like let's make a time step 0, time step 1, time step 2, time step 2. This is just like just enter the room, like didn't make any decisions, just like initial states. But maybe that the car is set up behind the door. But the guest, maybe the host know the whole this information, right? Because he set up the back door. But the guest doesn't have any information about the back door, right? And like he entered the room and the time step 1, he had to make decision. Like it can be like anything. Let's say he make a decision 1. It can be either like let's say equally like can be door 1, door 2, door 3, right? But I don't care that much at this time. And then let's say time step 2 is the host time. Like he will think in the behind the door. Okay, maybe he know that he choose a car or not. He know that he know everything. Like this is like unbalanced information like situation. The guests don't know about the back door at the
yeah. What is your argument?
My argument is that
you need to incorporate time.
Yeah, let me just finish. I want to explain because my argument is that the uncertainty of time 1 of winning probability 1/3 because he have no information about the back door, but once the time 2 the host open own door, it can be like anything. I don't care. At the time step 3, the uncertainty is reduced to 1 too, like help. Because of this given information, this is not the same. That's what I'm argument. This means that this because of this given information, let's say this is information is Y. I'm saying like mutual information. I think he will explain about this. The uncertainty of this uncertainty of winning car at this time is not same with this time because this is this. And I'm saying that this mutual information actually
Can I interrupt?
Yeah, it is not.
Can I interrupt?
Yeah.
So if we proceed this way, let's say, first time Monte Hall make a placement of a car behind our door, and then X1, which is the guest, makes a selection, and then Monte Hall open up a door, and then guest make the decision,
Right.
final decision.
Switch or not? Yeah.
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 So that's we have done
Yeah.
already.
No, but like my argument is that you can just apply the probability action because it's time invariant.
Why not?
Because let's say that this X is the probability of winning the car at time 1. For the guest, like he will thought that okay, I know that 1/3 probability I win the car. But after this time 2, he know that the information is given that one of these is not car. So at the time 3,
That was considered in the conditional probability.
yeah, I'm but like
So
okay.
I'll make a decision.
Okay.
Have a seat. I think we have considered the time in this way, and then we have considered the conditional probability. So all have been incorporated into the probability. And then you have you can make an objection, but try to write down what we have so far, and then since it is a line by line imputable, so you can dispute, make a dispute. This line is not correct because of this and this reason. Then we will consider. Okay, sounds good? Fair? All right. Okay, so now I will move on with our lecture. And all right. Okay. So this is about Claude Shannon. Basically, he has passed away in 2001. Basically, he has written up this landmark paper, Mathematical Theory of Communications, 1948. And basically, this has laid the foundation for information theory. And because of this paper, we have a digital age today. In this paper, he talked about ones and zero as a basic measure of information, right? And he had a theorem proving there exists fundamental limit in communications. And that one is quantified as entropy, the information measure. And then basically you can learn more about him by visiting this Bell Labs homepage. But I checked yesterday, it doesn't work anymore. So you can find the Wikipedia page on Shannon, and then you can read more about it. All right, so here novel perspective that he introduced in the field of communication was this. So there was a message. Let's say if you have a message could have a semantic meaning, right? So if someone says that there is a Ethereum 2.0 merge happening, and then someone interpret this as, okay, time to buy Ethereum. So other person says, okay, it's time to sell Ethereum because going for POS, proof of stake, is no good. Proof of work is best. So information here does not mean that, okay? Does not mean those semantic meaning. those semantic meanings is going to be different to the listener with a different background. You will interpret differently. But it doesn't mean that. So here, information is to mean it is a measurable. It's the amount of measure. I mean, so it's how big A is bigger than B. That type of measure we are talking about. So this is when he talk about information, he talks about the size of the message set that can be over a noisy channel with almost no errors occurring at the receiver. That's what he means by information. So information, he's trying to say there is a limitation in the amount of information that can be transferred from one location to the other. And that notion is called the capacity. So the capacity of the channel, so here channel is to mean noisy channel. So if you send a message from transmitter and then it arrives to the receiver, because of the channel errors introduced during the transmission, the received signal will have some noise in it, right? And then the Shannon's capacity means how much energy, how much information can you transfer over this noisy channel almost error-free. That's what the meaning of capacity here. We will spend the whole semester proving basically this is a single statement. Okay, so we are approaching this little by little. Okay, that's what we are going to do. So we would like to define the size of the message set. Okay, so message here is to mean some object or some digits, and basically the size of the message set that can clearly send from transmitter to the receiver is the capacity, and that we will define mathematically. So M here is the size of this message set, and then any monotonic function we can apply. For example, log. If M1 is greater than M2, then log M1 is greater than log M2. Okay? So this is a monotone function, right? Log is, and then we can apply that. And then when we use log base 2, then this becomes bits. Okay, so he is introducing this basic unit called bits. So bits means log of 2 of size of the message set. That is what it is. So for example, if you think about 4-bit register, how many information or how many messages can this 4-bit register hold? So that's the question. Basically, this is a bit register. So each one can have either 1 or 0, right? High state or low state, right? In a transistor, for example. So if you have 4 of them, then you could represent 2 to the power of 4, which is 8 messages. Okay. Then applying this to base 2 logarithm, then log 2 of 2 to the power of 4. So that is how many bits? That is 4 bits. Okay. So that is 4 bits. And that is what we call by amount of information. So 4 bits for 4-bit register, 3 bits for 3-bit register. Okay, so that's what it is. And then Carver and Thomas also has given an axiomatic definition of entropy. So basically it tells you that this type of entropy makes sense. That's what's the meaning of this Cabo and Thomas problem 2.4. Okay, and so here is the big picture view of a communications channel. In the middle, there is an erroneous channel. What you transfer at the input of the channel, at the output of the channel, what you get is the noisy receive word. So how you clean up this noise? Basically, that is the job of channel coding. So channel coding, what it does is it increases the redundancy of information and use this redundancy information at the receiver so that receiver can correct these errors that has occurred during the channel transmission. So 뭐라고요? 밖에서 하는 소리인가? Okay. So that's the job of channel coding. And then once you have done the encoding, then you have to do decoding. And then there is also source coding. Source coding. So source coding is compression. Okay? If you have, for example, a file, there are lots of redundancies in it. And then if you go through this compression operation, then the number of bits to represent this same source can be reduced. So that's the job of source coding. So it is removing the redundancies. And then at the receiver part, you have to decode it. You have to do the decoding. So you have to uncompress so that you can get the original signal back. Okay? And then going further to our left, basically, you have analog information, analog source. Analog source need to get sampled and then quantized. After you have done quantization, then you can do the bit representation. So for example, let's say you have 8-level quantization done. How many bits do you need for each sample? 3 bits, right? And then if you send these 3 bits at the speed of a millisecond, right? So what is the bit rate? 3 times of 3,000. So 3,000 bits per second, right? So that type of operation is right here. So this is like A to D sampling, analog to digital sampling. Once you have done, you do the source compression so that you can remove it. So let's say after you have done source coding, maybe the rate has become half, right? 1,500 bits per sec, things like that. And then when it comes to channel coding, you again increase the basically you add redundancies, right? So if you add, let's say, half the redundancy, then it goes back to, after you have done channel coding, the amount of bits has been increased by twice. So this becomes 3,000 bits per second again. And then you send it over the channel, and then you receive the erroneous word, and then you do the decoding, and then you do the uncompression, and then you regenerate the signal. So that's the general process of communication system. Here we will focus heavily on this part, channel coding part, in this course. We will actually design some channel code that can correct errors happened during the channel transmission. And this part, analog to source sampling and quantization, this is the stuff that you learn in electrical engineering sophomore class, signals and systems, and so on. So we are not going to deal with this part, right? We are going to deal with this part very heavily in this course. So in this part, most things are abstract, so mathematical version of the channel. So the channel is going to be described by random processes or random variable. So you send bit 1 with the probability of 1/3, the bit is flipped and then it received as a 0 or vice versa. That type of notion is introduced, used as a channel in this class. Okay. All right. So that's that. So here is the starting uncertainty and entropy. So entropy is very important. Let me tell you this. In this course, the most important part is chapter 2 and 3. Rest of them is application of this notion that you learned in chapter 2 and 3 for different problems. So it becomes easier. Chapter 2, mastering chapter 2 is very, very difficult. So just like a Monte Hall problem, it looks very, just like the probability rules that you have to apply. When you listen to it, it looks reasonable, but when you comes down to applying it, there is a problem. Okay, so it's the same thing. The definitions, everything are very, very simple, but when it comes to apply it by yourself on the board, when you want ask you to write it down, then you start to have a problem. So this is very, very important. Chapter 2. Okay, so pay attention to this. Okay. So this very, very abstract mathematicals, so you have to pay attention, okay? So this English summarization after we have proved things, that's very important to keep in mind, okay? All right, so entropy is a measure of uncertainty. And then entropy is a measure of randomness, okay? On the occurrence of an event. And then again, we are not going to deal too much with mathematical subtleties, okay? So we will assume everything is countable sample space, okay? So that you can assume that output is just a singleton set. So output, you can apply the probability. It's okay for this, okay? When you just don't need to talk this with the mathematicians who are majoring in this, okay? So majoring in probabilities. But then they will talk about, what is the Borel says, sigma field and so on. No need for this, okay? So we will, we have tons of new arguments, even with this, discrete arguments. Right, discrete output. So your sample space is countable sample space, even though it is uncountable, right, continuous. You just need to define some of the sets that we really want to investigate, like the one that we considered set A and B, and then sigma field based on that, right? So that's all we need, okay? So I will use outcomes, and then I'll apply probability. That's okay, okay? Don't make a fuss out of it, okay? Because it is not important, right? So for each outcome, we apply P1, P2, Pn. There are n outcomes, right? And so that's what we call distribution, okay? Distribution, okay? And entropy is function of distribution. Okay. If you give you distribution is given to you, you can calculate the entropy. How you do that? Apply the log. Okay, log of inverse probability. Okay, log of inverse. Why do you inverse? Okay, in order to make the non-negative measure. Okay, when you apply log pi, then pi is a number between 0 and 1. Then you take log, then it becomes negative, right? You don't want that. So that's why we are doing this. All right, if pi is smaller than pj, since we have taken inverse probability, so log doesn't change the relation, which one is bigger, right? So log 1 over pi is going to be greater than log 1 over pj, okay? So what does this mean? Okay, Shannon has this in mind. Okay, So that means what? If this is so, then pi, which is a smaller one, smaller event, has a small probability. But Shannon says those event that has a small probability carries large amount of information. That's what he's saying, okay? And then information is uncertainty, okay? So uncertain event, so for example, imagine yourself living in Los Angeles. How many of you have been in Los Angeles? None of you? So it's not a good example. So anyway, in Los Angeles, the weather is always sunny. Okay, do you think people listen to weathercast? They just ignore it because they already know it's going to be sunny, sunny, sunny all the time, right? So they don't care because there is no information. So, but suppose that you live in London, right? All kinds of weather, right? Sunny, very rare, right? Gloomy, and lots of clouds, wind, all kinds of weather. So people have to listen to weather forecast, right? So uncertainty means information, okay? So, and the less probable event has a larger information. That is carried by this logarithmic measure, okay, with the inverse probability. So less probable event means larger uncertainty. Now you can accept me, right? So, sounds good, right? More probable event, like sunny all the time, carries almost no information, okay? Smaller uncertainty. The sure event, tomorrow there will be sun in the morning. Sure event almost. Carries zero amount of information, zero uncertainty. Okay, so information means uncertainty. Uncertainty means information. Okay? So definition of entropy. Entropy is average measure of uncertainty of a distribution. So distribution is these n numbers, vector of n elements, okay? And if the h here is the definition of notation of entropy, okay? I want to find out the entropy of this distribution. That's what this means, okay? And then it's a function only of distribution. Okay, so distribution given to you, you can calculate entropy. Okay, entropy in previous page was what? Can it be negative number? Non-negative number, right? So average, so this one is doing what? That is information that we defined previous page. Log of 1 over pj's, which is non-negative, right? And then you do this operation. Multiply each one by pj, and then take the summation. So what is this? Average of information. Average. You are taking the average, right? Expectation, basically. Expectation of this function. Okay? Log of 1 over pj. Okay? So this should be non-negative as well. So this is always greater than y equal to 0. Okay? When do you have this entropy equal to 0? Can you give an example? Sure. How do you create a sure event given the notation here? Yeah. So you said P1 is equal to 1, rest of them all 0. So it's a fair distribution. Its entropy is 0. Okay? All right. So uncertainty is the amount of information, that is the number of bits needed in representation. That's where we are getting it. Number of bits that you need in representation. We will get to this later on. Okay? More uncertain event carries more information. I have covered that. The sure event carries 0 amount of information. We have covered that.
정보의 총량이라는 건 이해했는데 그 필요한 개체수라는 건 이해를 못했어요.
잠깐만, 뭐라, 필요한 뭐?
언설턴티는
어.
정보의 총량이라는 건 이해를 했는데 그 언설턴티가 표현하는데 필요한 비트수라는 건 제가 이해를 못했어요.
아, 그거는 example 하면서 이해합시다. Okay. So that's the part that we have to do it with a couple of examples. Okay. Right. So the sure event carries zero amount of information. Okay. And a binary source generating 1 with a probability 1, then 0 information. The binary source generates 1s and 0 with equal probability. Now I'm starting to answer your question, right? So there is a binary source. Binary source generates 1s and 0. Equally likely, it says, okay? Equally likely. Then each event carries the same amount of information, and then the source generates 1 bit of information. How do you do that? Because since you have asked, so there is a source generating 1 and 0 with the equal probability, right? And then the probability is this one, right? Half and half. All right. Then in this case, what is the entropy? So entropy is a function of distribution, right? We said this is the distribution of this source, 1s and 0, half and half, probability half and half. Then what is the expected value of this? So or the average, or the entropy. Entropy by the definition was this. Was this, right? In previous page, that was the definition, right?
언설턴티라는 개념이 왜 나오게 된 건가요?
언설턴티? 언설턴티라는 개념이 왜 나오게? 가만히 있어봐. 지금 아까 질문이 뭐였었지?
그러니까 지금
이게 저기 엔트로피의 총량이 왜 언설턴티냐고 물어본 거였었지?
방금은 그 언설턴티가 그 표현에 필요한 비트수 저게 이해가 안 됐었고 지금
필요한 비트수. 표현에 필요한 비트수.
네네네.
오케이. 표현에 필요한 비트수. 왜 엔트로피가 표현에 필요한 비트수냐? 그거를 지금 이 example로 해서 보여주려고 해요. 잠깐만 기다려주세요. 자, 그러면 요거를 하면은, 요 서메이션은 사실 어디서부터 돼요? 1서부터 2까지네. 그럼 그냥 써보면 되겠네. PI가 half라네. 그죠? 그 다음에 로그 2에 인버스 오브 half니까 2네. 그죠? 이렇게 쓰지 말자. 1 over 1 half. 이렇게. 그죠? 그리고 똑같은 거 반복이네. 그죠? 똑같은 거니까. 이거죠? 그러면 얘는 로그 2의 2. 그러면 1. 얘도 1. 1 두 개네. 그리고 half씩 곱했으니까 얘는 1. 1 비트. 이거죠. 그러면 여기 이 랜덤 베리어블을 표현하는데 필요한 비트 수는 1비트라는 거예요. 그게
저는 그리고 또 언설턴티는 어떻게 보면 좀 부정적인 개념이잖아요. 불확실성이라는. 근데 정보는 제가 생각하기에 좀 긍정적인 개념이거든요. 근데 왜 언설턴티를 정보라고 말하는지 이해가 안 돼요. 불확실성이 왜 정보인지.
그것도 아주 재밌는 질문인데 내가 그러면 어떤 랜덤 베리어블을 사용해서 가령 S 같은 거를 사용해서 누구한테 메시지를 전달하려고 해요. 그러면 불확실성이 하나도 없는 랜덤 베리어블 가령 S 대신에 P라는 랜덤 베리어블을 사용했다고 봐요. 프로버빌리티가 1.0이고 0이야. 이걸로는 상대방한테 메시지를 1비트라도 보낼 수가 있어요, 없어요? 그 질문하는 거지. 얘는 슈어 이벤트 아무도 리슨 안 한다니까? 맨날 일인데 뭐 누구 I don't care지. 이제 그래서 얘는 어때요? maximum uncertainty 아니에요? 내가 뭐가 나올지 몰라. 그러면 listen 해야지. 뭐가 나올지를 알지. 얘는 안 봐도 뻔하잖아. 제로 정보. 얘는 맥시멈 정보.
그러면 방금 말씀하신 걸 토대로 생각을 해보면 정보는 뭐랄까 이거를 해석하기 위해 필요한 양이라고 생각을 하고
그거를 이렇게 하지 말라고. 셰넌이 세멘틱 미닝 같은 건 집어치우고 size of the message set. 얼마나 많은 비트를 보낼 수 있느냐로 매저합시다. 그래야 아규먼트가 없잖아. 듣는 사람마다 다 정의가 다른 것 같고는 이렇게 디지털 에이지 같은 거를 만들 수가 없다라는 거지. 그냥 딱 계량적으로 할 수 있는 걸로 그걸 통일을 해갖고 얘기합시다. 그리고 이렇게 했을 때는 이런 정보를 저장하는 데는 트랜지스터 하나면 끝납니다. 바이너리 스테이트 on, off 트랜지스터 하나면 저장이 끝나요. 그 얘기 하는 거야. 그런데 이거를 얘기 나온 김에 조금 더 익스텐드를 하면 바이너리만 갖고 얘기해요. 조금 어려운 거 좀 주세요. 그러면 네 가지 경우가 있어요. 그런데 얘도 정보를 하나도 없게 하려고 그러면 아까 우리 학생이 한 대로 여기다 probability 1 주고 나머지 다 0 주면 아무 정보가 없지 얘는. 근데 얘도 정보를 maximize 하려면 어떻게 하겠어? maximum uncertainty. 뭐가 나올지 제일 모르는 디스트리뷰션이 뭐야? 4분의 1, 4분의 1, 4분의 1, 4분의 1. 이렇게 줘버리면 정보가 maximize가 된다. 오케이, 땡큐. 그리고 여기다 넣으면 몇 비트가 나올까? 이거를 엔트로피에다가 넣었다? 2비트 나오겠지. 그죠? 2비트 딱 나오는 거죠. 그러면 2비트가 맥시멈이래. 오케이.
이퀄 디스트리뷰션일 때 가장 언서티티가 높다고 말할 수 있나요?
말아? 크게.
그러니까 어떤 경우에 쓰든지
네.
프로버빌리티가 이퀄 디스트리뷰션일 경우가 가장 엔트로피가 크다고 정해.
그게 챕터 6인가 7 문제야. 이제 막 앞서가고 있어. 챕터, 그러니까 maximum entropy is achieved with equal distribution. 근데 항상 그런 건 아니고, 가령 내가 파워 컨스트레인트를 줬어. 가령 신호를 이렇게 쓰지 말고 이렇게 써보자고요. 1, 1, 플러스 3, 마이너스 3 이렇게. 그러면 신호의 얘가 앰플리튜드라고 생각하는 거야. AM 신호에. 트랜스미션 신호의 앰플리튜드라고 생각해. 그러면 앰플리튜드의 제곱. 그지? 이거 뭐라 그래? 에너지라 그러잖아. 그러면 트랜스미션 에너지를 1로, 에버리지 에너지를 1로 했을 때 maximize entropy 해보세요. 라는 문제가 나올 수가 있는 거야. 그냥 여기에 이 네 가지를 정보를 생산하는데 똑같은 에너지가 들어가면 이게 뭐 맥스마이겠지. 근데 I'll give you constraint. Keep the amount of energy to be equal to 1. 그치? 그랬을 때 maximum entropy를 어떻게 해야 합니까? 구할 수 있습니까? 그거는. 그러면 옵티마이제이션 문제야, 이건. 그런 것들을 우리가 이 인포메이션 티어리에서 바로 그런 거 하는 거예요. 근데 말을 하다 보니까 이제 시간이 다 조금 진도가 적게 나갔는데 뭐 좋은 질문이 나와서 진도 그까짓 거 뭐 천천히 가도 돼요. 뒤에 가면 비디오 있으니까 그것도 여기 와가지고 이런 얘기하는 게 더 낫지. 비디오 그대로 여기서 다시 할 필요가 없잖아, 내가. 난 뭐 다 아는 건데. 우리 학생들 공부하게 만드는 거, 이게 필요한 거잖아, 그지? 사고의 과정, 생각하는 방법. 천천히 생각하는 게 더 빨리 간다. 내가 말하는 게 그런 것들이거든. 대학교 2학년, 4학년 때까지는 시험 빨리 보는 게 시험 빨리 잘 보는 사람이 장땡인 세상이고, 대학원서부터는 천천히 사고를 틀리지 않고 하는 사람, 그리고 새로운 문제를 맞닥뜨렸는데 답을 알려주는 사람이 없기 때문에 자기 스스로 답을 찾아가야 돼요. 즉, 그러려고 그러면 첫 번째 했던 내 과정이 맞나 틀리나 검증해 보면서 가야 되거든. 스스로. 누가 안 알려준다고. 그랬다가 막 논문을 10페이지를 썼는데 처음에 가정이 틀려갖고 마지막 결론이 딴 거가 나오면 어떡해. 그러니까 확인하면서 가는 건데, 확인하는 방법은 딴 거 하나도 없고 라인 바이 라인으로 쓰라는 얘기야. 아규먼트를. 스테이먼트로 쓰라는 거야. 그게 내가 그래서 누구죠? 무크에 올라온 Mathematical Thinking, Introductions to Mathematical Thinking. 그거를 꼭 해야 돼. 그래서 자기 자신을 자꾸만 슬로우 다운 시켜야 돼. 하나씩, one by one. 그래야지 모르는 문제를 풀을 수가 있어. 누가 답을 안 가르쳐 줘도. 그거 없이는 풀 수가 없어요. 그게 only way야. 오늘 거기까지 할게요.